Okay, so we have discussed some of couple of simple examples. We have covered some sort of basic rules that we're going to deal with in C. But something that is more important to cover before we delve into more details is, again, what is the running environment of C? For example, Eclipse IDE or Visual Studio or any other compiler or even online GDB we have been using in lectures. All of this has the same concept. We said from the first lecture that C is a combined language, right? Not an interpreted language. So here I show the different stages of how really the source code that you write, for example, the hello world we wrote yesterday, is going to be at the end executed by the machine. First thing that you really write in an editor, right? So Eclipse, for example, is a text editor. You can really open any text editor and write a C program, it doesn't matter. And this editor is saved on a disk. And then if you run compile or build in Eclipse, first of all, you need to pre-process your text, right? So this is called preprocessing stage. And we will see right now really what do we do in preprocessing. But it's very preliminary processing of your source code. And then you want to compile it. And compiling includes assembling and then compiling, like generating the zeros and ones, which are also stored in the disk as a binary program. Then finally, once you run this program through Eclipse, or you double click it in Windows, for example, your operating system is going to load your program into the memory. But before this, if you have multiple files, similar to what we have in Lab 0, for example, we have the main file, the header file, the source file of the add function, but we also have our main in addition to our unit testing in another file. That means my program is composed of multiple files. In our simple example yesterday in Hello World, it was just 3-4 lines, single files, very simple. But in a real kind of industry or in a real project, you should structure your project to have multiple files because it's better organized. But at the end, you need a single binary, right? So how can you link all these files together? The way this works is that the compiler has a stage called linking, or it's the linker, that really combines all the source code in all the files of the project and gives you a single binary. Good. So going into some more details, well, editing is simple because you just write your source code in a text editor. For preprocessing, an example of preprocessing that if we go to our simple program here, this is my program, but we are leveraging the implementation of two functions that we didn't use. And we said yesterday this is possible because they are implemented inside the C standard library in Studio H, right? So in fact, scanf and printf are implemented inside this. And we tried yesterday, if we comment this out, the compiler is going to complain because these functions are not recognized. Good. The preprocessor, well, doesn't want really to deal with header files and includes and looking for source code somewhere else. So the preprocessing stage, what it does is it looks for any include here, and is going to replace this line with all the source code inside Studio.h. It's just simply making the actual, so here what we're saying include, which is a single line, is in fact including all the programs, all the source code of the program inside the header file. But you don't do this because this is better human readable, right? But for machine, well, I want everything that you want me to compile in front of me. So the preprocessor stage, what it's going to do is look for every include and then replace it with the actual source code. So when the compiler executes the source code, first line is include Studio.h. What is Studio.h? In the C standard library, which is in your, I don't know, in Windows it's C, then 2 colons and slash, and then GCC, where you really combine your C tool chain, or you define it. Then you will find the definition of Studio.h inside it. Go ahead, open it, copy it, place it here. Good. And then in addition to this, if you did any defines, static defines, also they are going to be replaced with the actual variable. That's something we didn't try it. So this is for preprocessing. Automatically execute what? Automatically execute. This is the first stage. And then, as I said, it replaces all the includes with the actual source code and try to do, well, various text replacements. For example, in C, assume I want to define a variable that is called size, but I want it to be static and I want it to be visible for everyone. So there is a parameter called define in C that allows you to define size to be 10. And every time you use size, it means it has a value of 10. Good. What the preprocessor is going to do is, well, take size, in your source code and replace it with 10 because it's a static constant value, right? So it makes it easier also to process. Preprocessing is a very simple and dumb stage, so it's not really the interesting part about compilers. And then we have the compilation stage, which takes the source code into assembly and then from assembly into what we call object file. Every single source file you have in your program is going to have its own object file. For example, cutest.c, which is part of your lab0 files, is going to have a cutest.object file. Well, lab0.c, I don't recall the exact name of the file. It can be add function.c or anything, which is the actual source code, is going to have its own corresponding object file. So every single source file would have a corresponding object file after the compiling stage. And then the linking comes in, combines all these object files into a single bind. This stage is called linking. So if I look back into what happens in, again, Eclipse IDE or any C tooling chain, I have the preprocessor. It takes input a C file, and it outputs a C file as well, because the output from the preprocessor is nothing other than a source code still, but just replacing the includes, as we said. And then this is going to be fed into the compiler. The compiler is going to give me an assembly code. I don't know, well, I would believe you don't know assembly yet because you haven't covered this in 2DI, for example, but assembly is nothing other than the instructions, like the instruction set architecture we had in our first lecture, the interface between software and hardware. We gave the example of ARM and x86, right? So you write low-level instructions in the format of what this is called the assembly language. And then the assembly file is going to be, well, it's going to be processed by an assembler, again, part of Eclipse IDE, for example, and gives you the object file. Here, as part of my project, I might have multiple object files equal to the number of .c files I have in my project. All of these need to be combined. So I feed them to the linker, and then the linker take all of them, put them into a single executor. Good, and this is the one that once I click or run, the loader would take it, place it to the memory. Is that clear? So why do we care about this, right? Well, you care about this because it's very important to understand really how your program is being processed by the compiler. For example, you might encounter problems if you have multiple files in your project and you're working, for example, with friends or you're working with a team in a company, and then you come up with a function name. Your friend comes up with the same function name. So you define the same function twice in the same project, but in multiple files. When the linker tries to combine these object files, it finds multiple definitions of either the same variable or the same function. Well, this is not allowed in C. You cannot define the same variable twice. Then it's going to complain. Figure out really what is the problem. Well, you need to understand this process. Good? Is there any question? Okay, so again, I'm all of my detailed example here. This is more or less the same example we covered yesterday, which is a low level C. I give it to the preprocessor. The only difference is include studio.h is going to replace really with the code of studio.h file, as we said. And then the compiler will take the preprocessed file and give you, here I'm giving you an example of an assembly code. So this is what I meant by assembly. For example, sub ESP is the stack pointer. Don't worry about these things for now. But simply the sub means a subtract operation of certain register with a certain value. Move means, well, move a value to a register. So it's a very low level kind of language to deal with the machine. Before the invention of high level languages, in fact, this was the only way of writing programs to machines, right? And usually in some universities, to for example, I used to teach a second year digital design course. Students used to write assembly programs to program an ARM embedded processor. So you can still, up until now, write assembly programs to control at the low level your embedded processor. Good? But we don't really care much about the actual syntax of this. What we really need to understand is the compiler takes a very high level language. It's better for human readability and ease of code, but it's not understandable by the machine, and transfer it into something that is lower level. It's very hard for a human to come up with this program, right? This is why it's easier to write here. But the machine, so that, well, the dilemma is this. It's easier for us humans to write high level, but, well, it's very hard from the machine to really parse this. It's very hard for us to really write low-level language, assembly, or even zeros and ones, but this is how the machine understands. So this is really how the compiler is important. The compiler is basically a translator of different languages. In one side, there is the high-level programming language that we understand. On the other side, there is the zeros and ones that the machine understands. Good. And then the assembler takes this assembly code and gives you the actual zeros and ones. This is the language that the machine understands. Anything else is just an abstraction that humans came up with, right? But computers don't understand anything other than zeros and ones. Good. Which is the importance of digital design course that you guys are taking to GI. And then the linking takes multiple source files. This is one, the object files, and then link them together into a single executable. Good. And then the loader later on, when you try to run your program, the loader takes it from the disk, places it in the memory, such that the CPU would read the instructions from the memory one by one and execute them. Does this make sense? In a microprocessor course, for example, you might be writing or kind of designing this microprocessor and then load some instructions to the memory and see how you can read them, interpret them, and execute them. For example, let's say here this zeros and ones, like the second line, or maybe the third line or the fourth line is corresponding to a subtract operation. So what the processor will see in the memory is a series of zeros and ones. I read it. How do I know it's a subtract operation? Does anyone know? How would the processor interpret this, for example, line as a subtract operation? Yeah. Yeah, exactly. And well, what defines these kind of patterns or fields? We have said this in that Tuesday lecture, right? That's your ISA contracts, right? But thank you. So basically, it's again the contract between you, between the software and the hardware is what is keeping all of this story intact, right? So the processor sees only zeros and ones, but the processor is implementing a certain ISA that means, well, 0, 1, 0, 1, 0 is a sub operation. So you should really pass it to your ALU, which is doing a subtractor. And your second field is your first register or your first value that you should subtract. The second one, the second value, etc. Right? Does this make sense? Is the story now clear what happens in a real program and how you execute it?